Today we are continuing with the seventh video of our series, Statistical Testing using R. And this is the before last video of this series, so I'm really excited to be able to covering measurement errors today. So without further ado, let's start. Measurement error analysis is essential for understanding variability, consistency, and agreement in data, especially in fields like healthcare, psychology, and biology. Measurement errors occur when observed values differ from the true value, introducing inaccuracies. These inaccuracies affect reliability of measures, making it crucial to assess them. Three widely used metrics to evaluate reliability and agreement are the Intraclass Correlation Coefficient, also known as ICC, Bland-Altman Plot, and Coefficient of Variation, which is also shown as CV. So don't think when I say CV it's the cross-validation here, it's the Coefficient of Variation. And we will be learning about all of these today. So let's start with Intraclass Correlation Coefficient. So this ICC quantifies the reliability and consistency of measurements across multiple raters, sessions, or instruments. So unlike Pearson or Spearman correlations, which we learned about in the two last videos, like the before the previous video, let's say, which measure the association between variables, ICC is ideal for situations where values are grouped and we need to assess their agreement. There are different types of ICC based on how raters or measurements are structured, the specific model, one-way or two-way, and assumptions about fixed or random effects. In healthcare, ICC is commonly used to assess consistency between raters. For instance, suppose multiple radiologists are diagnosing the same set of MRI images for brain tumors. ICC can help measure the consistency between these diagnoses, allowing us to understand if diagnoses are similar enough to be reliable. Now, time to implement this in R. Let me first write the name of it. Intraclass Correlation Coefficient. Let's insert an R cell. Now we need to install that packages IRR and say library IRR. We set the seed as 1, 2, 3. If you have the IRR library, you don't have to install it. By the way, let's see if I have it. I don't have it either, so I have to install it. Okay, and then we'll create our data frame. Since we are again using R norm, I set a seed. Then inside R norm we have number of samples. The mean, let's say 5, standard deviation 2, sales rater 1. Then we have rater 2, which is 10 samples, mean C. Let's say 6 main BSD2, then rater 3 is 1, 10, mean 7. Okay. After this, we can calculate the ICC. CC data as model we will give two-way. As type we'll say agreement. Then as unit we'll give average. After that, we can see the ICC result. Let's see. Okay, great. So first of all, model two-way indicates a two-way model, which assumes that the ratings are crossed, so each rater rates every subject, and the two-way model considers both the variability due to differences between subjects and the variability due to differences between raters. In a one-way model, each subject would be rated by only one rater or by different raters who do not consistently rate every subject. This is in contrast to our two-way model here, where each subject is rated by the same set of raters. For example, in a study where each patient is evaluated by only one unique rater, we would need to use a one-way model. And for The one-way model measures the variability between subjects relative to the total variability without attempting to separate out variability due to differences between raters. It focuses on whether the subjects themselves are distinguishable based on their ratings, so rather than whether raters are consistent with one another, which we due to this we use the two-way model here. And then the type agreements means that this we are calculating an agreement ICC, so this measures the extent to which raters give the exact same score rather than just being consistent in ranking subjects similarly. Agreement ICC is typically more stringent than consistency ICC, as it requires the raters' scores are nearly identical rather than simply correlated. So let's see. For agreement, when we need exact scores to match between raters, we use it, and when we need relative ranking and minor variations in absolute scores are acceptable, then we use consistency. So, for example, employee performance evaluations would use consistency, but diagnosing patients where exact severity scores are critical, we need to use agreement. Also, let me make this 5 because it's already random, so we might want to make it similar. And then the result tells us here that there are 10 subjects, so patients, and 3 raters. So ICC-A3 is the intraclass correlation coefficient for agreement with 3 raters. In this case, it's calculated as minus 0.46. ICC values typically range from 0 to 1, where higher values indicate stronger agreement. However, in this case, the ICC is negative, which is unusual and often signals poor reliability or even systematic disagreement among raters. A negative ICC can occur when the variation within raters is greater than the variation between subjects. This suggests that the raters are not consistent with each other at all in this scenario. So basically, ICC values can normally be interpreted as below 0.5 poor reliability, 0.5 and between 0.75 to 0.5 moderate reliability, between 0.75 to 0.9 good reliability, and above 0.9 excellent reliability. So here it's extremely poor agreement, which is expected because it's a random data. And then we have the F-test, which is in this case 0.683. And this F-test checks the null hypothesis that the true ICC is equal to 0. A high p-value in this case means we fail to reject the null hypothesis, so we say that the ICC is equal to 0, but we can't even say it's even negative. So the confidence interval is including 0, which means that we have a wide confidence interval from minus 212 to 0.85, which is very unreliable and unprecise. And since we have 0, we can't reject the null hypothesis. So since the upper bound of the confidence interval is still below typical acceptable values for good agreement, this further supports the conclusion that there is very poor agreement among the raters. So let's see. Now we can also plot it, but it's not really relevant in this case to plot. So I can just show the randomness here to you. So this was the plot I put in my article. We can see here that the rater scores are so different, they don't align for each patient, so it's kind of a really random scattered situation, so we can expect the ICC to be negative in this case. So let's see. Normally, but if you want to interpret, each vertical grouping represents the scores given by each of the 3 raters for a single patient, and the closer the dots are for each patient, the higher the agreement between raters, and large spreads within the groups indicate less agreement between raters. For instance, if some raters consistently score much higher or lower than others, the ICT value would also be lower. And then I think that was also. Let's continue with the Bland-Altman plot. Okay. Let's see. The Bland-Altman plot is a graphical method to assess agreement between 2 sets of measurements from different raters or instruments. So it plots the difference between measurements against their mean, allowing for visualization of the magnitude and pattern of disagreement, as well as any systematic bias like consistent over or underestimation. So this is pretty cool because it's just visualization and we create a plot. This is ideal for comparing two devices for measuring the same attributes such as blood pressure. By plotting the differences between the devices' readings for each subject, we can observe whether one device consistently over or underestimates relative to the other, which might suggest the devices aren't interchangeable. So let's implement this in R. Let's see. We have our device 1, which we'll again call our norm. Say 10 samples, mean 120, standard deviation 10. Now we'll make the other one so that a little bit higher as a mean, so that they won't be interchangeable. And 3 ST10. Then we'll now calculate the mean values. For this we say device 1 plus device 2 divided by 2. For differences, we say device 1 minus device 2, and then we plot it with ggplot. So we'll create a data frame for mean values and differences. Then for x values we will give the mean values, for y we'll give the differences, and then see, we'll create a scatter plot. Then we will create horizontal lines. First one representing y-intercept. Get the mean of the differences. Let's make it of about turquoise. And then line type, let's say dashed. And then we'll give another horizontal line by intercept. Now we'll say mean differences and add 1.96 multiplied with standard deviation of the differences, and then so it's like a confidence interval. We'll get the boundaries. Then let's make this color maroon. And then do we need anything else? Oh, let's make the line type dotted because let it be different. And lastly we'll give the lower boundary, which is the same. Oops, I was writing in the wrong part. Intercept. Get the mean of differences, subtract from the mean, this time 1.96 multiplied with standard deviation of differences, as color, for consistency give maroon again, and line type also because of consistency dotted. And then now we can add some labels. For title, let's give Bland-Altman Plot. Then for x-axis, let's give mean of device 1 and device 2. Then let's as y value give difference and device 1 plus device 2, and then that would be all for the Bland-Altman plot. Now let's see. Okay, so now this is our plot. So in this plot, each point represents a subject and compares two measurements, in this case from device 1 and device 2, by plotting the difference between the two measurements on the y-axis and the average of the two measurements on the x-axis. This allows us to visually inspect how similar or different the two measurements are across subjects. So the central line, which is the turquoise dashed line, represents the mean difference or bias between the two devices. In this plot, the mean difference is close to 0, which suggests that on average there isn't a strong tendency for one device to consistently measure higher or lower than the other. A mean difference close to 0 here indicates that the two devices on average are in agreement, but doesn't mean they agree perfectly for each measurement. And then we have the 95% limits of agreement, which are shown as the maroon dotted lines. They are calculated as the mean difference plus or minus 1.96 times the standard deviation of differences, and these limits helps us understand the range within which most differences between devices' measurements are expected to fall. And then in this case, the limits of agreement are around plus 20 and minus 20 on the y-axis. This means that for most subjects, the difference between device 1 and device 2 is expected to lie between minus 20 and plus 20. And each black dot represents a subject's measurements, so the x-axis position of each dot is the mean of the two device measurements for that subject, and the y-axis position is the difference between the two measurements. So we can say here that most of the points fall between the generally agree within the range of plus minus 20 units, and we can say they produce comparable measurements. Plus, there are no points significantly outside 95% limits of agreement in this plot, which suggests that there aren't any extreme outliers. If there were points outside these limits, it would indicate subjects where devices disagree substantially, which might raise concerns about the consistency between devices for these cases. And all these imply that device 1 and device 2 might be used interchangeably for measurements within this variability tolerance, although the plus minus 20 unit range should be considered when assessing suitability for precise applications. Okay, now it's time for our last measurement error method, which is the coefficient of variation. So CV is a statistical measure of the relative variability in a set of data. It shows how much variation or spread exists in relation to the average of the data. So CV is calculated as standard deviation divided by mean multiplied by 100. It's so simple. And then in medical and scientific fields, repeated measurements of the same quantity like blood pressure, glucose levels, or heart rate are often taken to ensure accuracy and reliability. For example, if a glucose level test is done multiple times on the same patient, ideally all measurements should be close to each other, indicating consistency. And even if we have different samples, so different means, still taking the different values, still taking the proportion would give us a general measurement. And here low CV means the measurements are close to the mean and have low variability, indicating high consistency. High CV means that measurements are more spread out around the mean, indicating lower consistency and more variability. So now let's test it. Testing it is really simple. I'll just write CV and then let's insert an executable cell. Glucose levels 10, 112, 9, 3, 13, 15, 4, 10, and we say, we just use the formula we've talked about. It's really simple. You take the standard deviation, divide by mean, and then multiply this whole calculating with 100. Then we look at the CV. Here we see that the CV is approximately 1.71. So this is less than 5%. We can say that the glucose measurements are very consistent relative to the mean. This low CV suggests that the repeated measurements have minimal variability, meaning the measuring instrument or process is likely reliable and produce stable results. In clinical settings, such low variability is often desirable, as it implies that measurements are precise and can be trusted. So that was all from this video. Let me summarize it before we end this video. So the Bland-Altman plot visualizes the agreement between two measurement methods or instruments, identifies biases and limits of agreement. So it gives the, as you remember, the bias, so the mean, and mean on the x-axis and difference on the y-axis. Then it gives the mean as the mean of differences as a middle line, and then it gives 95% confidence interval. And then, so nothing more to say for this. For this we need two sets of measurements from the same subject, so paired data. And then mean difference line indicates average bias. To repeat, 95% limits of agreement show range within which most differences lie, and outliers indicate potential disagreements. After that, we have the Intraclass Correlation Coefficient, called the ICC. It quantifies consistency or agreement between raters, sessions, or instruments across multiple measurements. So the data requirements here are multiple sets of measurements, usually from multiple raters or sessions, and it requires balanced data if using more complex ICT models. And then we have the coefficient of variation, which measures relative variability as a percentage of the mean, indicating precision in repeated measures. We just need a single set of measurements or repeated measures of one variable. So here lower CV, mostly less than 5%, indicates high consistency and precision, while higher CV suggests more variability, indicating less precision. And this is used for assessing precision in repeated measurements, especially with different units or scales, because we are looking at the proportion. And that was all. In our last video, we'll be talking about the hormone assays and how we can do calculate statistics related to hormone assays. So see you there. Till then, have a great day and take care. Bye.